Hi everybody, welcome to my 9th video on beams where I'm going to introduce the concept of bending stresses in beams. If you want to know something else about beams or about mechanics of materials in general, feel free to check out any of my other 40 or so videos. So bending stresses in beams. Alright, so when we take a beam, alright, I'll just take my eraser, it'll do good for a beam, and we bend it by some force or some moment. You can see the top is under tension in this case, and the bottom is under compression. So we can imagine there's going to be some sort of stress. All right, sigma. All right, so previously we had like an axial bar, and you pushed on it, and developed a stress sigma. All right, the same case here. All right, top tension, bottom compression. Do the other way, vice versa. Bottom tension, top compression. All right. So we need to kind of develop an equation, right? What is sigma equal to? We like to know this in terms of, common variables that we can find. So I'm not going to go through a full derivation of how to find this formula. I do that in one of my bonus videos, from fundamental principles and geometry all the way up to the equation. This video lets us go off our intuition. So let's imagine we have a beam. Okay, so I've taken this beam, I've drawn it thicker, or quite thick, and it's basically got some sort of loading on here, and then in reaction to this, we're going to have a bending moment. We already should know that. Bending moment M. Alright, now there's another important concept that we need to consider here, because when I put some sort of, other load on this beam, there's a point or an axis in this beam where there's absolutely no stresses. Alright, and you can intuitively think that's just going to be the very center of this eraser. Or if I flip the eraser, it's still going to be the center. Alright? Doesn't matter which way I stress it. I can stress it this way. Alright, the very center, or we can say right through here somewhere, there's going to be no stresses. Alright, it's neither moving apart nor together, so no stresses. And that's something unique for each cross section, and we call it the neutral axis. So I'm assuming in this case that I have a square beam. So cross section like this, the neutral axis is going to run right through the center like that. So I'll call it neutral axes. Alright, so this means that our bending stress, it's not just independent of where you are. It depends on where you are on the beam. So we're going to take an arbitrary term, well, not so arbitrary, which is used to describe upwards directions, y. Alright, so a distance y above the neutral axis. Alright, so that means sigma depends on y. Alright, sigma is proportional to y. So we'll just find a bunch of things it's proportional to and then collapse it into an equation. Alright, because when we're here, no stress. As we go up, we're going to get more and more stress. Alright, and it's linearly dependent on y. Alright, now how much stress you have, well, that's going to depend on the bending moment, right? How much twist is this beam developing in reaction to this? So the harder this beam twists back, the more, the more sort of compression or tension there will be at the top. Alright, so we can say that sigma is proportional to the bending moment. Okay, and there's one more thing it's proportional to. There's probably more things you can think it would be proportional to, but it's only proportional to one more thing. And that's basically the resistance, or the capacity to resist twisting. So for different cross sections, we have the most simple cross section, a square. Alright, you have more complicated cross sections like I-beams, T-beams. Each one of these has a different capacity to resist the same amount of twist. Alright, so you can imagine this one here would have, if you would twist it, it would have a different capacity to resist twist than this. This one has a higher capacity to resist twist than this one. Alright, and it has to do with the moment of inertia, I, or the second moment of area. Okay, now it's not directly proportional to it because the higher the capacity to twist back, if you will, the higher the capacity that this piece has to resist twist, the less stress there's going to be. So it turns out it's inversely proportional. Alright, now using a combination of these three, we get our formula, sigma equals to my over I. Alright, now there's one more thing I kind of need to say here. When we develop all these sort of notations, we assume a positive bending moment. You might know what that is. It's when a beam is bent in such a way that it makes a smiley face, alright? Smiley face, it's happy, yay, positive, alright? Positive bending moment. And in positive bending moment, if we take this beam, alright, here's our neutral axis, and we'll go up a distance y, we're going into a region where there's compression. Alright, so the stresses are going to be negative in that piece. So nothing about my tells us if it's negative, so we need to add a negative sign here. And now if we would go down, if the beam's in positive, the y would become negative, and that would cancel out this negative, and our overall stress would be positive. That makes sense. At the bottom we have tension. So that's just a little bit of notation you put in there, just to cover the mathematics of it all. Well, mainly for this course, we're just going to take a look at this equation without the minus sign, and then just ask ourselves, is it in tension or compression? And then go from there. Alright, so what's the distribution then of this stress in a beam? So let's get ourselves a profile of an I-beam. Alright, now where's the neutral axis of this? Because y is measured off the neutral axis. Alright, so in our case, the neutral axis is going to be right through the centroid. Alright, now how do you actually find the neutral axis? The neutral axis is the centroid of the piece. Maybe it's a good idea to write that down. The neutral axis equals to the centroid. Alright, so this is, well, actually not strictly true, because if you have different materials, it could be, it's a little different, but for most situations, this is true. Alright, so you're just going to go about finding the centroid, and that's your neutral axis, and that's where you're going to measure your y from. So what's the distribution of stresses? Alright, so when y is 0, it's 0. So let's just make an axis here and plot this. So as we go up in y, it becomes negative. So let's just assume this side is negative, starting 0, and it's going negative. Now it's going in a linear fashion because this is just to the power of 1, alright? Just like that. When we get to the top, we reach our maximum stress. Alright, that's interesting to note. When you bend something, the very top has the maximum stress. Alright, and then as we go this way in the negative y direction, so assuming that this side is positive and this is negative, this is just going to go linearly, alright, in this direction. So that's basically a stress distribution, if you will. Alright? So when you're asked to calculate the maximum stress in something, you're never going to say, oh, about, this far up, that's a maximum stress. No, you're not going to want to, you're just going to want to pick the very outside of your shape. That will give you the maximum bending stress. Alright, so that's about what I got to say for this video. I hope you enjoyed, and I'll see you in the next few videos where we explore this concept in greater detail.